to everyone live here and to everyone on Zoom, and welcome to a seminar or talk about QCut or quantum circuit knitting on FiQCI. Well, just to get started, let's talk about circuit knitting basics. So, what is circuit knitting and why one want to do it? So the basic idea is that you split a large quantum circuit into multiple smaller pieces. So as you can see here, with this picture, you have a large circuit and then you split into multiple smaller ones. A very, a simple diagram, but gets the basic idea across. And with this, you can, on more technical terms, you can simulate a large QPU on a bunch of smaller ones. And this way you can essentially increase the qubits you have available to be able to run large algorithms and actually solve some useful problems. And this also has applications in parallel quantum computing, where you can then distribute all of these smaller circuits into multiple different quantum computers and run them in parallel. So then one might ask, well, how do you do this? So circuit knitting can essentially be split roughly into two categories: gate and wire cuts. And they are very much what the names say. Gate cuts, they cut a 2-qubit gate into a group of these single qubit local operations. And wire cuts, they split the circuit from some empty spot in the wire into these like two independent parts, where on both sides of the cut location, you insert some operation. So I think at least in the gate cut part, it's like clear that these are just some single qubit gates. But then here with wire cuts, the yellow box is a measurement or some basis measurement. So you first apply some gates to transform into your wanted basis, and then you measure. And then the blue box is just you initialize some state. And though we will get more into detail in a moment of how this all actually works, but this is like a very rough diagram to get the basic idea across. So here first we're gonna focus on wire cuts. There's a lot of things going on the slide, but don't worry, I'll go through them and I'll try to make it as clear as possible. So all of circuit knitting basically relies on something called quasi-probability distribution simulation. Horrendous word, but it's essentially just a group of some operations or gates that have some coefficient or weight assigned to them. So you can it's like a probability distribution, but the weights can also be negative. And you can see one here, like in the gray box, you have some pair of operations and then some coefficient that is. So you can see it can also be negative. And these quasi-probability distributions can essentially be used to approximate other operations by sampling from this. So you can randomly pick a row from this list of operations and apply it on your quantum circuit instead of whatever 2-qubit gate, for example, you're doing. And then once you do that enough times, it will actually approximate the original circuit. So instead of having to do a multi-qubit operations, these are all just single qubit operations. And how this wire cutting procedure would progress is first you generate these experiment circuits, which means that in this split circuit, you insert operations from this list of operations. So you get one of these circuit pairs per one line on this list of operations. So as you can see, this has 8 rows. So that would correspond to 8 of these pairs. So 16 circuits or single wire cut. And also just if something is unclear, just ask. And then once you have all of those circuits prepared, you can execute them all. And then in the end, you can take all of those results to post-process them, and that will give you expectations values for your original circuit. So go through that once more. So you first split your circuit, where you get some locations where you want to insert operations from this distribution. You insert all of the operations from the distribution to get some number of new circuits. For example, for a single wire cut, you will get 16 circuits. Then you run all of those 16 circuits, and then you post-process the results, and you get expectation values for the original circuit that you had. Hopefully somewhat clear so far. So then just to go a bit more in depth into the steps. So again, for the step 1, generating the experiment circuits. So for a single cut, each line in this distribution gives you 1 circuit pair. So 8 pairs, 16 circuits. And for multiple cuts, you just basically take all the possible combinations of applying this multiple times. So then for n number of cuts, you would, how would I explain this easily? Since you can also cut your circuits into more than 2 parts. So let's say you want to cut your circuit into, I don't know, 3, 4, 5, so on parts. So then cutting your circuits into some number k parts, and then doing an n number of cuts. You can kind of stack these cuts, as well, kind of as many as you need to actually split the circuit into independent parts. You will get the k times 8 to the n number of total circuits. So, the number of circuits that you need to actually, approximate the original one with this method kind of scales fast. But for a small number of cuts, it's totally doable. And here are just some examples of like how partitioning of the circuits works. So let's say you have 2 cuts on your circuit here and here. So then you would want to split the circuit essentially so that the upper gates are on one circuit and the lower one is on another circuit. So then in the end you will have a circuit that looks something like this before inserting operations from the probability distribution. And you can also cut into more than 2 parts. So here's an example where you just cut a wire after each of these operations, and you get it split into 3 parts like this. And once you have generated all of your experiment circuits, you want to execute them all. And since they are all independent of each other, the order does not matter. You can distribute them into like, if you have multiple quantum computers available, you can distribute the circuits on those like in any way you want, and it doesn't matter. The one thing that matters is that you need to take enough samples from your circuits. So samples is, when you have your quantum circuits and you need to run it like multiple times so that you can kind of see how the results distribute across all the possible states. And for this, the number of samples you need from all of these circuits in total scales exponentially. So there's this thing called the gamma factor. We don't need to go into it too much, but it's just like essentially it's a factor of how quickly this number of sample scales, and it's always exponential with the number of cuts. So it's gamma to the power of 2n, where n is the number of cuts. And for example, for a wire cut, the gamma factor would be 4, and then you can see that it scales with that. And here epsilon is the error in the approximation. So let's say you want at max a 1% error in your approximation, then I think for 1 cut you need something like a couple thousand samples, which is less than how many shots you would even normally take on your any quantum algorithm you want to run. And then for the post-processing, once you have your results, so for each qubit you will have either 0 or 1 as the end state. You want to actually map the results so that 0 maps to -1 and 1 maps to 1. So this means that you kind of transform the end results into their eigenvalues. And this is just for calculating expectation values. And then once you have done that, you will apply this not super nice looking formula, but it just means that you take the sign of the coefficient for whatever operation you inserted from the distribution, and you multiply that by S, which is the measurement outcome from this inserted measurement, and you multiply that by all the other results from this circuit. So these 3 qubits that you would measure at the end that have been mapped to these -1 and 1 values. So essentially, you measure your qubits that you are actually interested in, and you multiply those by the sign of the coefficient times the result of the additional measurement that gets added from the wire cutting. And some people might have picked up that there are some drawbacks. So the number of circuits grows exponentially with the number of cuts made, and also generally with the number of parts that you cut the circuit in. And the number of samples also grows exponentially based on how many cuts you make, and then how small one error you want. This method can only give you expectation values. So if you are interested in the full probability distribution of your algorithm, this method is not meant for that, but only for expectation values. And how to combat these drawbacks? Well, for everything that scales with the number of cuts, the obvious solution is find use cases where you only need a few cuts to partition your circuit. You can also combat this by parallelizing all the circuits, between multiple QPUs. So you would use parallel quantum computing. For the samples, well, you don't actually need to take as many samples. Let's say the sample number was 4 million or something, which would be, kind of high of a number of samples to take, but you actually can inflate this in post-processing. So as long as you take enough samples so that the distribution of your results is clearly visible, then in post-processing, you can just scale that up, and the form of the results will still be the same. And that way you can, still do this with a reasonable number of samples needed. And as for only having expectation values available, that is still useful for many applications, such as optimization problems or finding some I'm blacking out. Well, finding some optimal states for whatever whatever you're researching. For example, I think QoA is a good example of this. And then getting to the actual thing that's in the title of this, which is QCut. And QCut is a Python package for wire cutting that I've developed here at CSC over the summer. And compared to other existing things, for example, QCut has their own circuit knitting box, but for that, wire cuts use something called reset gates and mid-circuit measurements, which are not available on all existing hardware. So this can perform wire cuts with no mid-circuit measurements or reset gates, and this also allows it to run on the current hardware available on the Finnish quantum computing infrastructure. The package is public, so if anyone is interested after this, you can go and try it out. And just like this. And just to give a brief overview of how QCut works. So first, user, you just make your normal standard QCut quantum circuit. And QCut defines this new custom operator called wirecut. You can insert this wirecut into your circuit, into the spot where you want to cut it from. And then you pass this circuit into QCut. And QCut will then decompose your circuit with the quasi-probability distribution that you saw earlier into all of these experiment circuits, and then pass those along into a quantum backend, or you could also pass it to multiple backends if you wish to do so. And then it will get the results back, and then QCut will post-process the results and pass the results back to the user. That's the very high-level overview of how QCut works. And at this point, I'll just do a brief example of how the workflow with QCut works. So just go here. So first, we're just gonna import all the things that we need. Then we define our quantum circuit, like you would normally with QCut. Then here is where the first QCut special thing comes from. So you insert this cut wire gate into your circuit, which will transform your circuit into this. So if we just compare these real fast, you see that in the cut circuit, everything after this point has been moved onto a new qubit. And that is denoted by this cut gate here. And then QCut, you can call this get locations and subcircuits function that will, it will actually separate the circuits into these separate independent parts. So here you can see that this part is actually the upper half of this circuit, and this part is the lower half of the circuit. And you can see that it also has added all the classical bits needed for the measurements. So this is now the additional measurement that gets added by wire cutting, and that is stored on this its own classical bits, so that we can easily use it in post-processing. And everything else is just stored on your, normally on classical bits, just like in QCut always. Then, here's just some more theory. So when you are actually sampling the circuits, you can get these probabilities for each line in the probability distribution based on the coefficients. But that doesn't really matter here, since all the coefficients were the same. So each circuit has the same probability, so we can just sample them at random, really. And here you can see the quasi-probability distribution. There's a lot of theory here in between, but it's a lot of the same things that we had in the slides. So I'm just scrolling through them, but again, feel free to ask if there's anything to ask. So here you can then get all of the experiment circuits, and I think we could actually print those real fast. So you can see all of the 16 circuits this makes. So yeah, so you can, for example, here with the first pair, you can see here again is the upper half and the lower half, and these are just look the same as in the original circuit, since the first line in the distribution is just the identity gate, and then or identity measurement, and then the preparing the zero state. So it doesn't really need to do anything. And then for the next one, you can see that there is an added X gate here for preparing the one state. So this this will give you all of the circuits that you need for, well, for doing the circuit knitting operation. And you can see here again also that you have, 8 groups of circuits, total of 16 circuits, and the groups are of size 2. And here we just take backend. Here at first we'll just use an ideal simulator. And then we can execute the circuits. Sorry, actually, for here we transpile the experiments. It doesn't really matter for the ideal simulator, but if you were using some actual quantum backend, then you need to transpile your experiments into the basis gates of your backend. And then after that, we can run the experiments. And then here's just described again the post-processing part. So we can then move on to see the overhead of this. So since the gamma value for wire cuts was 4, so then the overhead for this one cut would be 4 to the power of 2, which is 16. And then let's say we would want an error of 1% with 160,000 samples here. Well, again, doesn't really matter because we can just inflate that in post-processing. And then finally, we can define some observables. So this is just a list of qubit indices, which means that, okay, we want the Z observation value of the 0th, 1st, and 2nd qubit, and then a multi-qubit observation value of the 0th and 2nd qubit. And then now you can just pass the results, all the coefficients from the quasi-probability distribution, then the locations of the cuts that you placed on the circuit, and the observables on this estimate expectation values function. And it will then apply the post-processing and give you the original expectation values of the whole circuit. So then just for highlighting that they are actually the same as you would get from the original, it will run the circuit as a whole without circuit knitting, and then also with the ideal estimator. And then printing all of those, we can then see that with circuit knitting, we get almost exactly 0, 0, 0, and 1, which are the optimal ones. And then, well, this is also now just the same because it's using the same ideal simulator. But if we would run this on, for example, a fake backend, then these two would vary a bit from the ideal one, and we can actually do a demo of that too. So just go here and change the backend to fake, and then just run everything after this. And we can see that here is the expectation values that are from circuit knitting, then from just running the whole thing on the actual backend, and then the ideal ones, which seem to be wrong here for some reason now. No, I think it's just reversed them for some reason. Yeah, but you can see that they are still pretty much the same. So even with errors hardware, you can get quite close to actual expectation values. But this also, of course, depends on how well your quantum computer is calibrated. So the better your quantum computer, the better results you will get. And here on the noisy simulator, this is using the IQM fake Adonis, which is, if you are familiar with the Helmi quantum computer, it's kind of the IQM's fake noise model that is trying to mimic that. And here, QCut actually gives, at least for this case, a bit worse results than just running the whole thing normally. But for real hardware, I've actually got also some opposite results where QCut actually gives better results, which also would make sense since all the circuits you're running are actually, they have less qubits and they have less 2-qubit gates and less gates in general. So it would make sense that, at least in some specific cases, the error rates would be lower. And we can we can actually you can see some results from Helmi. So these are something I ran a while back. Helmi is not currently, I think, not currently calibrated since Lumi has been on a maintenance break. But these are from this summer. So it's the same circuit that I just run. And the ideal ones are again 0, 0, and 1. And QCut gets, well, actually quite a bit better results here than just running the whole thing on Helmi. So there is actually some, clearly some research to be done if you can actually use circuit knitting also for like some error mitigation purposes, for example. And then, of course, people want to know from actual applications of this. And well, of course, since this can only give you expectation values, you want algorithms that return expectation values, which are, for example, optimization problems or variational algorithms. So any VQA, or if you're familiar, for example, with QAOA, it's a very good example of this like graph optimization problem, or solving, for example, the max cut problem, which can be used, for example, the Ising model problems. And these are actually the two things I have at least seen where circuit knitting has already been demonstrated in some form. So QoA and quantum dynamic simulations. So these are already something that have been tried out on a small scale. And then with better, bigger hardware, you would actually scale these up. It has shown that it works and it gives good results. And then we can do a quick look into how you would do a QAOA with QCut, and what kind of results it gives. So I won't get too much into detail of like the theory behind QAOAs or the max cut problem or anything like that, because, well, unfortunately, we don't have time for that. But just again, we'll just import all of our things that we need. We will define a graph like this. And for this graph, we want to solve the max cut problem, which is basically how to cut this graph or partition this graph into two pieces so that we got the maximum number of edges. So here we can, just get some information about the graph, for example, the Hamiltonian that we can use to implement this on a quantum computer. Then there is just some helper function here. No need to worry about that. Then this actually creates the actual quantum circuits for this. You will see them in a sec. So here's the holding, the uncut version of the QAOA circuit. And then here is the cut version. So you can see that we have partitioned it here from the middle, so that this will be separated into two 3-qubit circuits instead of having to run a 6-qubit circuit. And then we'll just define the actual classical optimization part of this algorithm. So, QAOA is also a variational algorithm where you update these parameters of these Z and Rx gates here, and then you try to find some like lowest energy level or lowest value for this like cost function that you have defined for this circuit. And we can run them here. Again, we are using the IQM fake Adonis backend. This takes a moment with the simulator. But I think, well, we can already look at some results that I run earlier. So you can see the blue line is QCut, and then yellow line is just running the whole thing as it is. And then the red line is the actual like optimal minimum value. So you can see that we get very close to the actual minimum, and both QCut and the uncut version reach about the same value And we can see that actually QCut like flattens out or reaches the optimum value with less optimization routes than the uncut version. So again, there is clearly some use case here for, well, practical applications. But again, this is mostly a proof of concept, but still gives hope for the future that once we have, better, bigger hardware, that this would be an actual, valuable tool that can be used to solve actual problems. And here is, one other, I think this is probably, well, one of the best results. It kind of varies, how the graphs look, but this is like the best it can be, where there are pretty much the exact same. But, kind of depends. This is like what you would get always on the ideal simulator, but then sometimes even with the fake backend, you can see that it gives the exact same results. And then, well, you can go into more circuit knitting, but I would also be open to, if there's questions about anything before, then I would be open to those now before we move on to other things. I think the rest of the slides are mostly about some questions that people had asked in the sign-up form. So now if there is any new questions, then I would be open to answering. Or if there's any questions from the chat that I can answer now at the moment. Okay. Then I think we can move on. So now let's also look at gate cuts. So again, you remember from the beginning, gate cut means that we cut gate into these multiple 1-qubit operations. And well, it works the same way as wire cutting. You just have this like a bit different looking quasi-probability distribution. Well, this is not the whole thing, because it actually, for gate cuts, the distribution, of course, depends on what gate you're cutting, and also the overhead depends on what gate you're cutting. But for example, for CNOT gates, or any CNOT derived gate that is a CNOT gate up to some local unitaries has a gamma factor of 3, and a swap gate has the gamma factor of 7. And well, compared to wire cutting, it actually has a smaller circuit overhead. So this will, even though it's 4 lines, but since we have these plus minus ones here, this will be composed into 6, or a quasi-probability distribution of 6 lines. So number of circuits that you need in total actually scales, well, a bit slower than for wire cuts. So instead of having the k times a to the n, it scales as k times 6 to the n. But the thing with gate cuts is that you need mid-circuit measurements, which is currently still a bit of a problem for a lot of present-day hardware. They are available for some devices, at least for, I'm not sure if it's available on all of IBM's devices, but at least some of them, but they are still quite erroneous. So, it's again a question of, like if they are available, should you still use them? And that's about it for gate cuts. We won't get too much deeper into that, but instead I'll answer some more questions that people had asked in the sign-up form. So there was a question about like what kind of role does classical communication play in circuit knitting? So all of circuit knitting can, if you also allow classical communication, you can split it into these 3 categories. So the first one is local operations, which is everything that we just covered now. So wire cuts and gate cuts, which is sampling from the distribution. And there, the circuits are, completely independent from each other. You can run them in any order that you want, and you can do both wire and gate cuts. Then you can also do local operations and one-way communication. So then you would have, one of the circuits is sending information to the corresponding pair. So you need to communicate in one direction. And this can actually be implemented with classical processing between the pairs of circuits. So you don't need to actually have some, classical communication lines going between your QPUs. And this can at least as far as I know, this can only be used for wire cuts. And then you can have local operations and two-way communication. And this two-way communication then means that you need actual like real-time classical communication between your circuits. So then you need multiple QPUs that are talking to each other with some classical communication channel. And as far as I know, this has not been done anywhere yet, but there are papers out there at least. Again, from IBM, they have a couple of papers about this, I think. And I think they are planning on doing something with it. And this can be used for gate cuts. So then more about the one-way communication part. So you can do wire cuts with quantum teleportation. I hope people are somewhat familiar with quantum teleportation, which if someone doesn't know, it's just basically a quantum circuit where you can transfer a state from one qubit to another. So like in a nutshell version of what it is. And for this, you can actually see that the overhead goes down with the number. So K here is the number of cuts. So the overhead goes down with the number of cuts you make. And this is specifically like simultaneous cuts. So in this case, you can actually, instead of, independently doing, one cut here, another here, a third one somewhere later, you can actually, like reform your circuit so that all the cuts are kind of done simultaneously in the beginning at a single time slot, and then you can store some results on some ancilla qubits, and then use that to perform the actual like approximation of your whatever gate or wire you're cutting. And this basically transforms like the type of wire cut we saw earlier into cutting a CNOT gate. And this probably doesn't make much sense, which is words. So I have a picture of a quantum circuit here. I know looks scary and everything. I'm sorry. I tried to make it as simple as possible, but this classical communication circumventing topics are they can get out there quite fast. But here what you need to see is that these 3 qubits here at the start, these are like your actual like qubits that you want to do like computation or like these are like your circuit. If you would draw like your circuit like before the wire cut, it would be like these 3 qubits where you have these 2 operations on the first 2 qubits, and then this operation between the second and the third qubit. So again, it's the same simple circuit we had earlier. And then here in this first dotted box, you prepare a bell state for your teleportation circuit. And then now what you can do is you can actually teleport the quantum state from this qubit down here, where you can then use it, on the other part of your cut circuit. So instead of, if you would compare this to the previous wire cutting example we had, here we would insert the measurement operations, and here we would insert the state preparation. But now we can just teleport this state from here to here and continue our, life nicely. And earlier in the previous slide, I said that this method transforms the wire cutting into cutting a CNOT gate. So you can see that here circuits are actually, there's a CNOT gate in between them. So then you need to cut this CNOT gate. So then you are actually still doing the same kind of quasi-probability distribution simulation as you were doing with the gate and wire cuts before. But with this method, you can actually just prepare all of your bell states. You need 1 bell state per 1 wire cut. So you can actually prepare them all here in the beginning. And with the gamma factors, it turns out that it's cheaper to have like 1 decomposition that approximates like multiple bell states instead of having like in sequence multiple that approximate a single bell state. So by doing them all like parallel or not parallel, but like simultaneous in the single time slot here in the beginning, you can actually get a smaller gamma value and less of an overhead. And then, well, here you can see the rest of the teleportation circuit. So, well, I won't explain it, all the way through. But if someone wants to ask about it later, then you can. Then for the two-way communication, so again, scary formulas, not familiar words, but then with QCuts, you can also do them with kind of like teleportation through this like choice state, where this choice state is, well, essentially how you can think about it here is just some state that stores all the information from the action that your gate does into some quantum state. So from that quantum state, you can then basically get out all the information that you need from what the gate does. And again, here it turns out that multiple cuts, simultaneous cuts, are cheaper than multiple individual ones in sequence. And with this one, you can get this general form for cutting a gate. And this is for Clifford gates. Again, I hope people are familiar or somewhat familiar with Clifford gate group. But this is the overhead you get for Clifford gates. And for CNOT, you get this one, and you can see that it was the same one as it was before for the wire cut. And so someone might ask, since this is only for Clifford cuts, then how about for non-Clifford gates? And there are some decompositions also for non-Clifford gates, but those are only for like very restricted groups or very small groups of them. So there is no like general form. So it's still an open problem to find some like very, something that applies for everything. And it's not even clear if it's possible. And here again, very big scary looking circuit. But then here, the dotted box is preparing the choice state. And then the the first two qubits here are just your like actual like computation gates, and then this would be some gate that you apply like in between the two qubits here, but instead now you move it here in the preparation of the choice state, and then after that you take some measurements and then perform some like correction operator. And this is again quite advanced, so I don't think I have time to get like too much into the depth here.
Yeah, I have been thinking about this. Like, how do you actually prepare this choice state? Do you know about that?
I mean, it's this black box here. So you have some like you initialize the zero state, and then you apply these operations where U here is the gate that you want to cut. So let's say you wanted to cut a C0 state, then this would be a C0, and then you just these like operations in the dotted box prepare the choice state.
Like if it's between two devices.
Well, then again, let's say this was a C0 gate. This was what I was coming at. So let's say this was a C0. Then you actually again need to cut this C0 gate with the quasi probability distribution stuff and do this like well, it's called like simulated entanglement. So it's still, even though you are using some fancy, communication between QPU stuff, you still need to use the quasi probability simulation. But even though you're using that, you can get the overhead to come down with this method. So
okay, yeah, that's a good answer. Yes, yeah.
And for CNOT gate specifically, you can actually, instead of having to use the choice state, you can actually use a Bell state because it's enough for the CNOT, and it gets, a lot simpler here. But I think you can highlight here that you can see that there is actually communication between the circuits like in both directions. So from here to here, and then from here to here. So for actually to implement this, you would really need to have two QPUs where you have some classical communication line in between them where you can send like data in real time once it makes the measurement here and once it makes the measurement here. So this is, well, something that we will hopefully have sometime in the future. And then someone also asked about quantum communication in terms of circuit knitting. And well, as far as I know, at least for gate cuts, there is no at least like immediately obvious way you could use quantum communication for. I'm sure there's probably some way you can at least utilize it to maybe get the overhead down a bit more. But for gate cuts, it's actually quite simple. So you don't need any QPD quantum quasi-probability distribution simulation anymore. You just need to, let's say again, you want to cut here. So then you can just transfer the state from this qubit to this qubit through your hypothetical quantum communication channel. And then you can just run the circuits, normally. So you would just start with running this. And once you get to here, you send this state through the quantum communication channel to here, and then you can run rest of this circuit. Quite simple. Since you don't need to sample from any distribution, this actually completely eliminates the overhead. So the only thing, or the only overhead you might have is, whatever time it takes for your communication channel to send the state from one QPU to another, and then that might, cause some errors or something. But there is no need for any additional circuits, no need to take extra samples, no need for anything. So this would really be like the most optimal form for wire cuts. But again, quantum communication channels still a work in progress. But again, hopefully one day. But even though there are still there are already schemes for parallel quantum computing where you send stuff between QPUs and this would be implementable with those same schemes. Then one other question was, okay, then how do you find the optimal cut locations? Because then of course you wanna, if you would concern yourself with just wire cuts, you want to do as few of them as possible to get the least overhead possible. And then if you also add gate cuts in there, then it also matters not that you just do as few of them as possible, but also matters what gates do you cut? Because some gates have way higher overheads. For example, the swap gate has triple the overhead from a CNOT gate. But it really depends what kind of gate and what kind of cuts you want to make. So then how to find the optimal ones? So then, of course, what you want to do is minimize the overhead from the cuts. And how you can do this is you can transform your circuit into a graph. And there's a picture of this here. So for this circuit knitting, the single qubit operations, they don't matter. You can just drop them out completely. And then you can make this graph where you have two kinds of edges. So you have the green edges here, which are possible gate cuts. And then you have the blue edges that are possible wire cuts. And then all the vertices are basically qubits that, are taking part in a 2-qubit gate. So you can see here, you have a 2-qubit gate here, okay? And for both of those qubits, you have vertices here. Then again, you have a 2-qubit gate, and you again have vertices for both of them. So that's how that works. And then in addition, the edges, they are weighted by the overhead that this cut would impose. So then finding the best or the optimal cuts can be thought as partitioning the graph in a way where you minimize the total weight from the cuts you have made in the graph. So then you can just basically you would loop through possible cuts. You can check oh, okay, if I cut here, does it partition the circuit? It does not. Okay, we move on to the next possible combination. Okay, this actually partition the circuit. Let's save this for later. And then we can check the next combination. Oh, we found a new one, and this actually has a lower overhead. We actually want to do this, and then you just keep going until you have well, either you can check all the combinations, or you can just, let's say you can set some parameter like, okay, let's say if you get an overhead that is less than this, then stop looping through and then just use that. And there are some implementations of these methods. There is one implementation for just wire cuts, which is, I think there's a paper called QCut that describes their method. And then there is optimal cuts with gate and wire cuts which then describes this method here. Yeah. And then I think this might be the last question that was asked in the sign-up form. It was about parallel quantum computing. So like, how can you, or what are the applications of this for parallel quantum computing? So I would like to, for circuit knitting, it's less of an application for parallel quantum computing, as parallel quantum computing is an application for circuit knitting. So with parallel quantum computing, you can take down the observed QPU overhead that the user sees quite drastically. So let's say you have, if you would have 16 circuits and only one QPU, and you need to run all the 16 circuits in sequence on your QPU, that can, take a while, and it's not nice for the user. Well, let's say you have 16 QPUs, and then you can just, run all of them, in parallel on different QPUs and get your results back immediately. Then that is much nicer for the user, much nicer for any applications where you don't want to have to wait in queue for all these devices, or you don't want to have to wait for the previous jobs to finish. You just want to get it done as fast as possible. And then for parallel quantum computing, you can do that, where you just split one circuit into one QPU, which is this case here, where you have many smaller QPUs, and you distribute the circuit across them. Or you can also do something where you have a large QPU. Let's say you have a 5-qubit circuit and a 50-qubit QPU, for example. Then you could actually pack multiple of those 5-qubit circuits at the same time onto the same QPU, and then just run that or you could pack multiple of those 5-qubit circuits into a larger 50-qubit circuit, and then just run that packed circuit on your large QPU, and then that would also be, you're essentially running 10 5-qubit circuits in parallel on a 50-qubit machine. And then, of course, the most powerful way you could use this is by combining both. And well, this is of course something we would also want to do with, for example, circuit knitting, or for some variational algorithms, for example. And I think that's my slides. And now, if there is any questions or any points of discussion, then I think we still have some time for that. Well, we have 4 minutes left of the reservation, but I don't think someone is coming to kick us out. So yeah, so if there's questions or any discussion points, then, or if you just want me to explain something more, then please go ahead.
Sorry, yeah, I had a question. How does the error rate compare with gate cuts and wire cuts?
It's quite similar. Both of them. Well, I haven't actually tested this in depth, but I would assume that with gate cuts, it would actually reduce the error even more, because you are replacing a 2-qubit gate with single-qubit gates that are much slower error rates. Whereas in wire cutting, you are just replacing some empty spot in the wire with single-qubit gates. So yeah, I would assume that it's lower with gate cuts.
What are your next steps? this work?
Next steps, we actually have a demo of this like kind of quantum parallelizer. So the next step is to make QCut support actually like in some nice way to support parallelizing all these circuits between different devices. Yeah.
Do you think you would be able to also include some error mitigation techniques?
Yes, actually, even right now in QCut, there is a flag that you can set on like the function that runs the circuit, which is uses readout error mitigation. So it's very not that fancy, but it's there. But for sure, it would be nice at some point to have some more error correction models. And I think now that IQM is moving their software stack to QCut 1.0, so then I will also because this has been developed to work with IQM machines, so this has been using like their latest supported version. But now this will also be updated to QCut 1.0, and then with that, depending on all the features that IQM, for example, supports, then it would be nice to, for example, see if we can use the like QCut samplers, for example, where you can set this like optimization level flag that actually applies some error correction. But then I'm not sure if that is possible, if that is like doable or not. But if that is doable, then that would be nice. But I'm sure we can throw some error correction in there somehow. And you could also, of course, manually add error correction because you don't need to you are not locked in to running the circuits with the built-in function from QCut. You could actually just define your own, like, I don't know, for loop or something that runs them all and then applies error mitigation. Like you can also, you have control over that.
For example, these libraries I've been looking at, for example, this one QCut. So why Python is being used and not other languages for such libraries?
It's mostly because the like quantum computing software stack has been developed on Python. So QCut, Circ, Penny-Lane, everything is on Python. So it's kind of like basically every QPU you have out there, you can access it with QCut, and then with every tool you have, you kind of have to use it. But that's also something I've been thinking, that some of the like processing parts of this would of course be faster if you would write them like C or something like that. And that's something I've been thinking that would be nice to explore at least at some point. But at least the quantum parts are kind of, well, so who you ask if it's unfortunate or fortunate, but they're kind of locked into Python because engineers like Python.
Yeah, so the performance is not being considered. Like,
well,
is like more preferable, or me being more preferred than.
Yes, for now. And of course, with QCut, for example, I've tried to optimize it, as much as possible with Python. And it's, for example, like it's using numpy arrays and such, which are like they have been written in C. So, but it would be nice to, like, try to, I don't know, port at least some parts of this into like its own separate C extensions for Python, and then instead of, straight up doing Python functions, instead let's just call that extension and then it runs some C file. And like that would most likely be at least a bit faster. But then again, the post-processing here it's not very heavy, like especially with numpy arrays, like there is not really any considerable overhead from the post-processing. Like it takes like, I don't know, 1 second, 0.2 seconds even with Python running in a Jupyter notebook. So I think the most expensive processing part is actually generating all of the like subcircuits, because then let's say you want to make like 10 cuts in your circuit or something, and then you have, let's say you have 5 times 8 to the 10 of circuits, and you need to generate all of those. Then that can take a moment. But then that part would be nice to have in C, for example. But then it gets kind of difficult because the quantum circuit the objects that you're dealing with are from QCut and they are like a Python class, so it gets a bit difficult trying to use that from C. But I think there are some ways from Python where you can like define some like C extension or something that can actually like access Python classes. And there is also something called Python that I've been exploring with actually like tries to convert like most of your code and or compile it kind of into C code somehow and then run that. And if I guess we lost the screen. Oh, yeah. If we try to, I'm not sure if that can like support like accessing like Python classes. Do we have paper here? Thank you. I think there's some in the bathroom. But yeah, but it would definitely be like more optimal to have like the processing parts in C, but it would require some more tinkering and more research. Yeah. Actually, a very very valid question.
If I can also comment.
Yeah, sure.
Like, because I was just at the conference and then IBM there announced that they have been starting to use Rust.
Oh, really?
Yeah.
Oh,
Rust,
that's nice.
yeah, they were advertising that and they got some better results.
So what are like, do they have like some Rust framework, like kind of like QCut?
Yes, yeah, it's like
Oh,
somehow they started to integrate QCut so that something runs in Rust.
that's kind of cool. Yeah.
Yeah.
And I know at least, well, there is also the Microsoft's quantum computing stack, which is, I think, it's something called, I think it's technically called Q# or something, but I think it's written with like C# or something, or C++ or something like that. So
So is that a programming language itself? Or,
it's like, I guess it's technically called Quantum Software Development Kit, but I guess it's also kind of its own programming language. I'm not too familiar with that, but I think you can. I don't think too many things support that except the I think the Azure Quantum, or I don't remember if that's the name, but I think it might be the name. But I think the machines that are accessible from there also support this Q#.
My question is about applications. You mentioned quantum dynamics simulations. Have you implemented this?
No, so far the only like practical application demo I've done is the QAOA demo, and for the quantum dynamics application, I don't remember the exact paper name. I think you can find it if you Google just circuit knitting applications. It's like quite high up on the Google search, but it was they were simulating like some ground state of some molecule, I think, or something like that, and they were using circuit knitting for that. But I think, if I remember correctly, they also used gate cuts in their work. So that is something that wouldn't be right now possible with QCut.
So for the gate cut part, do you need to like decompose the gate into the Clifford gate and non-Clifford gate, or you can just cut arbitrary multiply unitary?
Well, you can easily cut an arbitrary Clifford gate, but then if you have some non-Clifford gate, then those don't have any like general decomposition where you can like plug some variables in and you get your distribution. But for those, like there are some like at least for some like non-Clifford rotation gates, there are some like some ranges of like degrees for which there exist is like decompositions, but they are not universal. So then like what method you need to use depends on the gate, and I don't think there even exist decompositions for all like non-Clifford gates. For example, I'm not sure if if, for example, a T gate has such decomposition.
So in general, you need to, like, if you have a multiply qubit gate, you need to decompose it into the basic Clifford gate.
I mean, yes, but then if you have some just like 2 qubit non-Clifford gate, then it's not possible to decompose that into just Clifford gates.
Yeah.
But then let's say you have some some multi-qubit gate like the Toffoli gate or something, then you could decompose that into a series of C nodes and some T rotations, and then you could cut like some of the C gates, C node gate, for example. Is there any questions on that?
There was a question, does using QCut introduce additional error rates?
Well, under research, that's like the unfortunately the best answer I can give right now. There have been some papers, for example, that I said from like applications to like the quantum dynamics and QAOA, or the QAOA paper. They this is again from memory, if I remember correctly, they were getting quite similar results to just running the algorithms without circuit knitting. Same for the quantum dynamics one. From my own research of just running some like very simple algorithms, I've gotten varying results depending on the calibration level of Helmi. Sometimes QCut seems to be a bit better. Sometimes it's the same. Sometimes it's a bit worse. So on average, it's about the same. At least something that has been consistently better with QCut has been readout error mitigation for some reason. So far, every time I've tried, this circuit knitting procedure with readout error mitigation, it has always given better results than just running the circuit as a whole and applying readout error mitigation to that. So there's clearly some research to be done here. But my hope, at least, is that you could use this circuit knitting to kind of reduce error rates. And it would also make sense for the errors to be at least a bit lower, since your circuits, they are smaller, they have less gates. So, and especially with gate cuts, you are like, in addition to splitting the circuit where you have less qubits and less gates, then you are also transforming some of the 2 qubit gates into single qubit gates that have way lower overheads, or way lower error rates. So so far still under research, but like my hope and initial results are at least very promising. Anything else in the forum?
No.
Right. Well, if there are no more questions, I think we can stop here. I can also hang out here for a bit longer if someone wants to ask something more or wants something to explain. But then for the people on Zoom, thank you for attending, and I hope you now at least have some grasp on what circuit knitting is, and maybe you want to go and try out QCut, and of course always open to feedback or any comments, or if you want to send me an email or I don't know, message on LinkedIn or something, then feel free to do so, and I will do my best to answer.